All right. So commonly, kind of how I got started to be real interested in UHPC was I do a lot of work with precast pre-stress companies as a technical service engineer, and they'd always ask me. They'd say, "Dr. Cook, can you come help me design some mixes? Can you figure out, you know, I have this strength criteria I'm trying to hit." And they're trying to look for this silver bullet to kill this big bad werewolf. And I would always, I'd always try to help them, try to explain to them, basic things about strength gain, and I'd always use rocket ship analogies, um, about like a 1960s rocket ship and how it launches and how different reactions take place, through the cement and the water and other, secondary cementitious materials and how they all react together and how accelerators and retarders and how everything kind of works together. And a lot of times that I'd show them things like, this is how you kind of get to a mix design like this. You got to really lower that water cement even more. Sometimes they would choke out and just have way too little of water, and their admixtures wouldn't work well enough. And so there was a lot of different things. I would try to help them design mixes. And what's really interesting is this UHPC. A lot of them would want me to help kind of design mixes that for that, and and they're always focused on the cost part of it. And it was always interesting, UHPC. We could talk about how it's the definition is 22,000 psi, the minimum compressive strength. And then, ASTMC 1856 has some standard practices for fabricating testing specimens for ultra high performance concrete. And so, this is a table I kind of put together, different tests that I've seen for UHPC that have been required over the years. And so some of the, common names, some of the standards, and then is this part, of ASTMC 1856. And so, in essence, if you're not very familiar with UHPC, typically in the field, a lot of times people will have a proprietary product where they just have everything already pre-made, and then they will put it, in some type of mixer, and they'll add a certain amount of water, and they'll mix it up. And typically, it takes a lot longer to mix up because you have a lot less water. And so whenever you kind of, and if you have better numbers than what you're seeing here, that's great. That's awesome. Just, if you have some better numbers, great, let me know. But these are kind of the ones that I typically see for the different components. There's a few things, I may have missed, just because of you can only put so much in a table at once. But typically what you're going to find is quite a bit of cementitious, whether that's cement. You're going to find usually some silica fume or metakaolin. A lot of times to make it more economical or more durable, you're going to provide a little bit more fly ash. And you don't see any coarse aggregate here, but you see a lot of fine aggregate. And then you're going to see a high range water reducer at a pretty high dosage rate. That's very common. And then typically you're going to see, if it's proprietary, a lot of times they'll actually have the still, either they may have it added in beforehand, the fiber, or they may have it added in separately. It just depends on what the product is. And so these, when I look at these mixed designs, it's kind of interesting, trying to think about the workability and how a lot of times, with this UHPC, it is self-consolidating concrete. Or close to it. And so it has some really unique thixotropic behavior. I'm really enjoying seeing presentations where people are really digging into that, because it is a little different than other self-consolidating concretes, and it is most definitely unique. But a lot of times with the workability, people use a slump flow. If you're not familiar with that, they invert a slump cone, and then they'll pull it up and they'll measure the spread. or they'll have like the flow table, like kind of like you see over here on the right. And that's kind of the two basic tests. A lot of times people start using mini table or mini slump test. I've been seeing that a little bit more often. And I think one or two of our presenters just kind of talked about that already. But what is workability in general? It's the ability to place or mix, place, consolidate, and surface finish. And that can mean a lot of different things depending on what your application is. Obviously, it just, different workabilities, you need different things. You also don't want things like segregation or poor finishing, or, if it's not flowable enough, or if it's too flowable. So there's always, the workability issues you just don't want. And I grew up a little different. I'm actually a fourth generation concrete finisher, meaning my great grandpa about 90 years ago was finishing concrete. And so my grandpa, my dad, and I, we all worked in the family construction company that only built concrete stuff. So we did that for years and years and years, and I really enjoyed it. And so now it's really fun to go back in the academic world and start doing research and teaching and construction technology and stuff at OSU. So it's and so it's really fun just to come out and just do different research. And whenever I'm looking at workability, especially through a mix design, just to kind of highlight some issues is what I'm going to do right now. Because one thing, whenever you're unlocking workability of UHPC, you got to understand what you're dealing with. You got to understand your mix design and what you're given. So probably the first one that should be very noticeable is water. You should obviously notice that, hey, this water to cement ratio is really, really low. And you may not think, if you just look at how many, per yard, how many gallons of water or how many pounds of water, you may not see, that's not really that much, but we're dealing with a lot of cementitious materials up here. So, the cement and the silica fume, whatever powders that are there, you're dealing with a very, very high amount of cementitious materials together. And so it really drives down your water to cement ratio. And, while I can talk, we can all talk about whenever you get too high of water cement ratio. Sometimes people talk about Kool-Aid, and you don't want to have watered down Kool-Aid. Maybe as a child, maybe your parent watered down the Kool-Aid a little bit so they didn't have as much sugar, or they didn't have and so it's kind of like that, where you don't want to add too much water, because then it's just not the right mix. It's not good. It doesn't provide those good strengths. And so whenever we talk about, having the right microstructure, concrete kind of looks like, in essence, a dense sponge in hardened state. And so you want your, cement particles, when they're tighter together, they're going to be able to, the hydration process with the water and the cement, when they react and hydration products form around the surface of those cement particles, they start interconnecting together. And obviously, the farther they're apart, the harder it's going to be for them to interconnect, and you're going to have lower strengths. You're going to have higher setting time, or longer duration of setting time, stuff like that. So, I think we all kind of, seen charts like this if you've been in engineering or anything like that, and you kind of understand there's, one of the probably the biggest parameters is water cement ratio whenever you're dealing with the strength of concrete. And so, this is kind of basic, a mixed design 211 that you can kind of think about with, as you start lowering the water cement, you get higher and higher strengths. And obviously this is for a conventional concrete mix, but I think we all kind of get that basic theory. And so that's why we're at these really low water cement ratios. But, what's a challenge with these low water cement ratios? Well, some of the challenges are, it's harder to thoroughly mix. You have to mix that water completely throughout the mixture, and that's hard to do. The cement starts clumping up and balling up everywhere, and all of a sudden you think that you have a coarse aggregate or something in your mix when you really don't. You have a lot of cementitious, you have fine aggregate, and so you really got to go and mix mix up really well. And once all that water is distributed, it's crazy how it changes into this SCC that we think of. So when we talk about lower amounts of water you mix, lower water cement ratio, you're also having a more narrow window of placement. So from whenever you're done mixing and it's all mixed together, to whenever you place it in the molds and the forms, you're going to have a much smaller window, because and so there's just a lot less water. So you're going to have a lot more rapid slump loss too. It's kind of crazy how quickly you can lose your slump loss. You can lose slump throughout just a very short amount of time. And so you got to be really conscientious whenever you're placing mixes like this. And then the last thing is to understand is there's a lot of high range water reducer, and so a lot of times with admixtures, especially to get that, a lot of times they need to interact with water, and to really be as effective as they need to be. I know, and so you got to be kind of careful to make sure you have enough water spread out so that the water reducer can do its job. And I'll talk a little bit more about that in a second. And so about each of these. So when we talk about mixers and mixing times, I believe there's another speaker right behind me that's going to talk a little bit more. But in essence, you're trying to get that water all the way through all that powder and all that sand, and that's a lot of surface area to get there. Sometimes it takes 30 revolutions more than a conventional mix. Sometimes it takes more than that. Sometimes there's mixers that just aren't as well suitable as others to produce this UHPC product. Typically you want something that has a high shear energy mixer, and you really want something that's going to provide a good uniformity to the mix. That's kind of the goal. So I learned very quickly you can overmix stuff too. So this is just an illustration. These aren't real numbers, but I've kind of seen I've seen numbers like this where all of a sudden, you start at the y-axis when it intersects zero of time. That's kind of the mixing when it stops mixing, whenever it's ready to mix. And then if you keep mixing, eventually this UHPC, you're gonna see a pretty quick where that window of mixing just there's gonna be a rapid loss of water, and slump's gonna go down quite a bit. And so it's kind of crazy how quickly that occurs compared to maybe a conventional concrete mix, which can take much longer than that. And again, when you have a lot less water, this is going to happen. Same thing with slump loss. Like I said, you may start out with a really good flow right when it gets out of the mix, and then over a certain little bit of time, maybe with the UHPC, it just starts going down quickly, where there's just the workability does. And then you can compare that to a conventional SCC where you really want to extend that workability a lot longer. And a lot of times you can get there, but again, when you start having these lower water cement ratios, the water in there, if there's not as much reaction with the water reducer over time, it's not as effective either. And if you lose water through evaporation and other things, so just kind of be aware of that. Another thing that really affects workability is the fiber dosage. So there can be all sorts of different fibers that you may, whether you add it beforehand or after, whether they're in bags, of product that they're already pre-bought, and you just add water to make you UHPC, or maybe you do your own mix design and then you add fibers then. It's important to realize the picture on the right is just normal concrete, but you can see the fibers that are in here and how they're all kind of interconnected, and you can get some really nasty looking mixes in just conventional concrete. And so whenever you go and you try to do UHPC, and sometimes these fibers can really impede the workability. You also got to be careful to make sure you thoroughly mix if you're going to be adding in these fibers, that you properly mix them right. And so again, that may require more additional mixing time. And so there's a kind of, like I said before, there's a tight window to kind of get these fibers distributed properly. So and a lot of times there's fiber type in the mixture, all those kind of balance each other out. So just kind of be aware of that. So one thing, and whenever you look at most of these UHPC mix designs, is they're going to have some type of high range water reducer. And it's usually going to be at a high amount. So if you don't know much about water reducers in general, here is over on the right. If we're just doing conventional concrete, and we do, maybe you have a mix that's neat, doesn't have any admixture. Maybe it has a 2-inch slump, but if you add a normal range water reducer, you might get get a little bit better of a slump, a little higher of a slump. If you add a mid-range water reducer, you might get even a higher amount. And then if you add a high-range water reducer, you'll even get, it'll become even more. And so this is just an example of if you're adding 5 ounces per 100 pounds of cementitious weight, this is something that you might get for a mix. And so it's really interesting with these high range water reducers, which sometimes people call them supers or plasticizers or super Ps or super plasticizers. There's a lot of different nicknames out there. And in essence, how they kind of work is cement likes to clump up, especially when it's around water. It'll clump up and it'll trap the water in there. And a lot of times you'll see little balls in the especially your HPC. And so what water reducers do is they change the surface energy around those cement particles and let them spread out. Okay. So why does this matter? Well, think about how you use a dryer sheet. So whenever you go and do laundry, and you take it from the washer, you put it in the dryer. Usually you throw in a dryer sheet, some type of fabric softener, not only to make your clothes smell better, but it changes the surface area of them. It makes it so that it removes the static charge, so that you don't shock yourself when you grab your clothes once they're coming out of the dryer. It makes it so that your clothes are actually softer, less wrinkled too. It makes it so that all the clothes kind of spread out. They're not clumped together still at the end of the drying cycle once they're dry. So that's kind of, in essence, it changes the surface energy of your cement particles so that they can flow outward more. They can spread out those cement particles. You can get the water. You don't trap a bunch of water in there. The water can be spread out better too. And so the term like water reducer, it doesn't actually reduce the amount of water in the mix, but it does reduce the amount of water required to achieve a certain workability. So just kind of, realize where that term came from, is from that. And so in conclusion, I'm just, trying to highlight some things that, I've noticed dealing with UHPC. There's other things I've missed clearly, but these are just things that, I'm kind of familiar with, that I've seen. You never, when I put this together, you realize very quickly, you never take enough pictures. But, the importance is to realize with UHPC is it's a high performing product. You're going to have a low water cement ratio. High range water reducers are there to kind of help with that workability, and you got to really do a good job mixing and making sure that that water is spread out thoroughly throughout your entire mix. And just realize whenever you're dealing with it, whether it's placing it, that you're probably going to have some slump loss a lot quicker than a normal conventional concrete or even on most types of self-consolidating concrete. So just kind of be aware. I'm just trying to highlight a few of those things. All right.
Okay. Thank you very much, Dr. Cook, for your practical and useful presentation. If people have some questions for this presentation, please use the Q&A. We have a couple of questions. So the first one is from Alfred, and he says, how do you deal with shrinkage issues at these low water to cementitious material ratios?
No, that's a great thing. So one of the challenges whenever you're dealing with low water cement ratios is you're going to have a lot more higher, and there's different types of shrinkage. So, one of the things is when we talk about autogenous shrinkage or chemical shrinkage, whenever you're using a large range of high range water reducer, a lot of times those particles spread out. Once they're not effective anymore, you may see some shrinking where those particles start trying to come together. And so there, and again, this is, there's a lot of studying that needs to occur. So don't try to butcher me on some of the, trying to explain that, but in essence, you're going to have some shrinkage because of the low water cement ratios. And so in essence, one of the things is you try to do the best job you can, making sure that your fibers do help some. Number two, you want to make sure that is this the lowest amount of water I can actually add in this mix. Sometimes you can get away with adding a little bit more water. It's not going to hurt your strengths. It may not. So just kind of be cognitive of trying to figure out where your mix is performance wise, and you may be able to add some water to kind of help a little bit with that too, so that you don't have as many problems.
If I may add to this, Dr. Cook, the first presenter, Dr. Mang, when she was doing her PhD, we also looked at mitigating autogenous shrinkage, which can be very, very high. The use of different SCMs can contribute to that, of course. But also you can consider using some internal curing. In our case, we used some saturated lightweight sand, but I know other people also have used super absorbent polymers, and there's quite a bit of literature on that, and that can mitigate autogenous shrinkage quite a bit without hindering mechanical properties. One more question from Sari Malak, who is wondering about the use of UHPC in the repair of structure elements. For example, the question is, could it be used to increase the flexural capability of a beam where you are adding to the tensile area some very thin UHPC like FRP, or maybe on the sides of the beams? Or is that not an application that UHPC has been considered for? What's your opinion?
Any of our panel could probably answer this, but I would. I think I've seen it is used as commonly as a repair material, and so I believe that would be a use for it. But anybody else have anything else that they'd want to add?
If Dr. Mang or Dr. Farah would like to add something to that, they can.
Yeah, actually replying to this question by Sari Malak, there are quite some applications for beams, as Kamal was saying, for flexural or also shear retrofitting, but also for confinement of columns or repairing of bridge piers, shear walls. It's becoming quite quite popular. As Wayne was saying, then the issue is also preparing the subgrade surface with an adequate roughening in order to guarantee the bond. But surely it's really the material to be in some cases for this retrofitting.
You can also consider and use as a stay-in-place formwork for enhancing transport property, cracking resistance, and even for protection of bridges. Okay, very good. Thank you very much, Dr. Cook, for your presentation.